All right, AP Stats. Let's do this. This is our last new content section for the year, and it's called Separable Equation. So this is a technique that you can use to solve a certain class of differential equations. So remember that differential equation is an equation that involves an unknown function and one or more of its derivatives. So a separable equation is a first order differential equation, meaning first order just means it only involves the first derivative. And it can be written in this form: dy dx equals the product of g of x times f of y. So if it can be written in that form, it's considered separable, and I'll show you why. So the process is that we are going to separate the differentials. So we're going to multiply the dx to one side, and then we can separate the factors of x and y, so that y is with its differential dy and x is with its differential dx. And then we're just going to integrate on both sides. On the left, we'll integrate with respect to y, so treating y like a variable. On the right, we'll integrate with respect to x, treating x like a variable. And we do have to remember to add a constant. And then, in some cases, we may be able to actually solve for y. Remember, y is our unknown function. So let's just go through a couple examples. I think that'll help you best. All right, so this is a separable equation that we're going to solve by separation of variables. So what I'm going to do first is multiply the dx to the other side. So I'm going to have dy equals x squared over y squared dx. Then I'm going to multiply both sides by y squared, right? And so on this side that cancels, and I end up with y squared dy equals x squared dx. And so now, once I have everything completely separated, meaning all the x's with its differential dx and y's with its differential dy, we're ready to integrate. And so on the left-hand side, we treat y like a variable, and on the right-hand side, we treat x like a variable. So I'm going to do just power rule for anti-differentiation here is going to give me y cubed over 3, and I need to do plus a constant. I'm going to call it c1. Over here I have x cubed over 3 plus a constant. Doesn't have to be the same constant, so I'm going to call it c2. Now, in general, I could just subtract c1 from both sides. That cancels on the left. And then I have c1 minus c2, but a constant minus a constant is just another constant. That all being said, I don't really have to put that constant on both sides. I just have to put it on one side. So all I really needed to write was y cubed over 3 equals x cubed over 3 plus c. And I'm done with part A. So this is A. And then part B, they give us an initial condition. Oh, you know what? Let's finish out part A. I said if you can solve for y, you should. And in this case, we can solve for y, right? So I'm going to say y cubed equals 3 times the quantity x cubed over 3 plus c. And so that's y cubed equals x cubed plus, let's say, a different constant. Call it c1. I'll just make a note where 3c equals c1. And then I'm going to take the cube root of both sides. So y equals the cube root of x cubed plus c1. All right, there's my answer to part A. So now we have the unknown family of functions. But for part B, they want us to find a particular solution. And they say when the initial condition is y of 0 equals 2. So B, we want to solve for that c. We know that y of 0 equals 2, meaning when I plug in 2 for y, I need to plug in 0 for x. And that should allow me to solve for C1. So I get 2 equals the cube root of C1. So I need to cube both sides. So 8 equals C1. So my particular solution is then y equals the cube root of x cubed plus 8. All right, and that's it. That's how we solve a separable differential equation in general and with an initial condition. Let's try another one. All right, so this one's a little messier. So I'm going to separate my differentials and my factors of x and y, and I'm going to do it all in one step this time. So in this case, I'm going to have, 6x squared dx is equal to 2y plus cosine y dy. All right, so once I have all the x's with their differential dx and y's with their differential dy, I'm going to be ready to integrate. So let's integrate on the right and the left. Now on the left, what are we going to end up with? Y squared plus sine y equals, on the right, power rule, add 1, so 6x cubed over 3 is 2x cubed. And again, I don't want to forget to add my constant to one side. So here's a case where y is going to just remain implicitly defined as a function of x, because it would be too hard to separate y out and isolate y. So we're just going to leave this as our final answer. They don't give us an initial condition, so we're not going to be able to solve for C here. But there we go. Our general solution is a family of functions to that differential equation. All right, let's try one more. Solve the equation y prime equals x squared y. So the first thing I want to do in this case is rewrite this in Leibniz notation, which is dy dx equals x squared y. Then I'm going to separate my variables, so dy equals x squared y dx, and divide over the y, so 1 over y dy equals x squared dx. Good, we're ready to integrate. So integral on both sides. Now on the left, the antiderivative of 1 over y is natural log absolute value y. And on the right, we get x cubed over 3 plus c. And this one, I am going to say we can solve. We can isolate the y, and we're going to exponentiate both sides by e. All right, so on the left now we have absolute value of y equals. Now, when you add exponents, we can write that as a product of powers, right? So we can say that's e to the x cubed over 3 times e to the c. But e to the c, that's a constant to the power of a constant, so it's still a constant. So let's just rename that. Let's say e to the c, we'll just call it another constant a. So absolute value of y equals a times e to the x cubed over 3. And then if I want to drop the absolute value bars, I can, but I need to do plus or minus a e to the x cubed over 3. And there's my family of functions. That's the solution to that equation. All right, folks, I hope it helped. If you want me to go over specific problems, throw them in the comments. See you soon.